Hello and welcome back. So we will start from where we left in the last class. So we left with a question, that is which one between the two-level system and a between a three-level system and a four-level system, which one is better in terms of laser action or a more efficient system. So I hope that most of you have figured out what is the answer. In case you have not, then the answer is here. So it is obviously the four-level system, right? So here we had the question, and here I have the answer, that is four-level system. So four-level system will work better. Why? The answer is actually hidden here. Okay. When I have to create a population inversion in three-level system, I need to pump it really hard. That means I have to pump in lot of energy, right? So if I have more number of photons going as a pump, that means I am putting more energy. On the other hand, because this state is not the ground state, so its population is 0, okay, or very near to 0 at the beginning. So as soon as the first first transition takes place from here and then quickly comes down here, I have a population inversion. So I have to really use low energy if I want to just get a laser output which is comparable to this one, only because this state is not the ground state and it is empty to start with. Okay? So I don't have to compete with a ground state population. That is why the four-level system is much more efficient, much more energy efficient than three-level system. And also the two reasons that we discussed, that it can be operated both as continuous wave as well as pulsed source. Okay? So because of these two, four-level system is always better. An example of four-level system, the most famous one I will mention here. We will talk about many more in the days to come. Neodymium yttrium aluminum garnet, or in short it is called ND-YAG laser, and even shorter term for this one is just YAG laser. Okay. So the four-level system is very common, and this is one of the most common laser that is used industrially and in scientific laboratories and everywhere. And we will talk about this in quite detail in the one of the following classes when we discuss about different types of lasers. All right. So I think we have enough fundamental and theoretical background about laser and laser action by now, with which we can start considering the actual practical depiction of a laser. Okay. So how practically we can get a laser, okay, so that we can start considering. So if I ask, what do you need to form a laser? Okay. So what will be the answer? If you are following the lecture, then you should be able to answer this. Okay. So the most important thing that you need. So, is an active medium. Okay. I mentioned about active medium in the first class of this week. Okay. So, just to remind you, this is the material that you are using, okay, where you can have say a 3-level system or 4-level system, which has those characteristics that is needed for showing laser action. Okay. So, not each and every material in the world can provide you all the characteristics. Okay. So, certain materials which can give you the the characteristics that is needed for lasing action, showing lasing action, and you can suitably manipulate that. You can use that as the active medium. Example, ruby is an active medium. Okay. So, if you take a ruby crystal and then you start pumping it, essentially you are creating the population inversion there, and after some time it will give you stimulated emission. Okay. And you can try amplifying that stimulated emission, and you can get an amplified output. Okay. And what do you need? You need a pump, because you have to create the initial excitation, correct. So, you have molecules in the ground state or atoms in the ground state, you have to pump them to the excited state and then let them decay to a particular state from where they will lase. Okay. So, you need a pump source, and that can be various type of sources. You can have like a flashlight, okay, a flash lamp, like what Myman used in his ruby laser. So, he used a flash lamp which was a broadband, like various different photon energies are there, different frequencies were there, and then pump it. So, the particular energy that is required to pump it from state 1 to the highest energy level is taken from that broadband flashlight. In certain other active mediums, say for gas laser, so we will learn about this, say argon ion laser. So, in those gas laser you use electrical discharge, okay, to as pump. Okay. So, that this discharge provides you the energy to pump it. So, you need these two. Okay. Now, what are the other things that you will need to get a device which will give you laser output? So, let us think about it. Okay. Now, let's try to do that. So, when we say that laser is an optical oscillator, a laser is an optical oscillator. So, what does that mean? That means that it will have a continuous amplitude. Okay. So, my drawing may not be that good, but just what I wanted to mean here is this amplitude is same. Okay. So, you have constant amplitude over any given period of time. So, that means this axis is my time, and this is associated with a time period, say let us call tau. All right. Now, this is in the time domain. If I look the same thing in the frequency domain, how does it look? Let me draw it over here. Okay. So, if this is my frequency axis and this is the amplitude, Then if I Fourier transform it into the frequency domain, then what I will see is this corresponding to a particular frequency, let me call it as nu 0. So, this constant amplitude oscillation will look like this in frequency domain. So, the width of this spectrum, which is also known as line width, is really small. It is very close to 0. Okay. So, this is what we expect from laser, okay. And actually it gives this. Now, let us consider a practical system, okay, because we are talking about oscillators. So, the oscillator that comes to our mind, if we start talking about any oscillator, is simple pendulum, right. So, something tied to the roof and okay. So, and you take a small string and put a mass here and leave it here, okay. So, bring it here and leave it. So, what it will happen? It will start oscillating, right, back and forth. So, fine. So, it will go here also in this direction, it will start oscillating. So, this is a classical example of oscillator, and suppose this is the length of this rope or thread, whatever you have or wire, then it will be associated with a frequency. So, this frequency that we know from our high school physics, it will be fine. Now, how will it behave as a function of time? So, if I look at the amplitude of this oscillation as a function of time, what we will see is something like this. Like this, okay. If we add this tips, we will see an exponential decay, okay. So, if you keep looking at further, you will see it is an exponential decay which scales as e to the power minus t by tau, where tau is the period, okay. So, this keeps going down and down and down, and if I look at the corresponding frequency domain picture, very similar to this case, I will see a spectrum like this when I see it in the frequency domain. So, this is nu 0. Earlier what we had a line spectrum having line width close to 0, okay, almost like a delta function. On the other hand, here I have the central frequency is the same, while there is a huge spread. So, the line width is much larger, okay. So, I have a broadband thing. So, what I have a tremendous loss of the amplitude with time, and then I have a spectral broadening. So, this is because of the friction, right. So, it is happening in air. So, it is having friction and slowly the amplitude is decaying. Now, if I could somehow prevent the friction or reduce the friction and prevent the loss, what will happen? This decay will be slight lower, and if I can completely make up for the losses here by something, I do not know what, but suppose there is a person here, okay, and suppose he is, standing there and just, it's coming and going back, and so he is compensating for the energy loss there. If you somehow can do that, then what will happen? So you can come back to the situation where you have continuous constant amplitude, okay, and again a spectrum having nearly 0 line width. So the question is, how do I compensate for these losses, okay, or how do I minimize the losses, okay? So we do it very cleverly, okay. So in order to get a final laser, I need to overcome the loss and get my output, laser output. So that is done in a resonator, okay, in a cavity which is formed by two mirrors, okay. So now if I put my active medium, say neodymium doped YAG, yttrium aluminum garnet, or say ruby. So this is essentially my active medium, okay. So this is my active medium, and then suppose I have kept a flashlight here. So flashlight is such that it is sending pump photons if you remember the picture that I showed in I think the second class, where you had this picture of the components of the ruby laser made by my man. So how was it? It was like, let me draw it over here. So you have a rod which is like a ruby crystal, and then you have a flashlight which is like a spiral, right. So this is the flashlight, which is like like a spiral, like you have seen those LED bulbs in your houses, which has this nice spiral kind of thing. So suppose you are putting a active medium, say a ruby crystal, inside that one, and then turn on this this spiral lamp, then essentially that is all the photons coming out of that spiral flashlight, it excites this ruby laser. All the light goes to the ruby crystal. Okay. So you excite the active medium by some photon source, that is my pump. So this is pump and this is optical pump. Okay. So say a flash lamp. Now what will happen? This will create the excitation in this active medium, and if there is a stimulated emission, suppose I have a 4-level system, right? Now suppose this is YAG active medium. So, it will create the population inversion, and then it will also create stimulated emission from there. So, the stimulated emission will keep coming. Now, if I just allow the stimulated emission to go away, then some amount of energy will go, but that will be very low. Now, what will happen if I trap them in this cavity which is formed by two mirrors such that both the mirror has 100% reflectivity. That is, whatever light goes here, it is reflecting back. Okay, so nothing is going out. So it's totally closed kind of system here. So now what will happen? This system, after pumping, it will at some point of time give you stimulated emission. That stimulated emitted the photons coming out of the stimulated emission will be coherent, okay, and they will be directional, and because of this directionality, whatever the photons that are going out in this direction, they will be all reflected back. So this will again reflect back, go through this system, and again hit it, and again it will come back. So there will be round trips, right? So the photons that are coming out as a stimulated emission, they will keep going. So now how it will work? So this spontaneous emission that is actually triggering this overall stimulated emission causing the laser, this spontaneous emission which are taking place in this direction, that is along the axis. So suppose I am calling this one as axis of this whole cavity. So this is my axis which is perpendicular to this mirror. Okay, so these are mirror M1 and say M2. So this axis is perpendicular to the plane of this mirrors. Okay, these are suppose flat mirrors. So then those spontaneous those photons which is coming out of the spontaneous emission, which are going in this direction, they will also create stimulated emission. If they are taking part in triggering the stimulated emission, then they will lead the photon which are coming out of stimulated emission in the same direction, and then they will keep going and back and forth between these two. So this is developing a directionality totally. Those photons which are coming out of spontaneous emission, but they are off axis, suppose they are going in this direction, they are going out of the cavity, they are lost, okay, and we do not really care much about that, okay. Maybe a little we will talk about that later. So this off axis spontaneous emissions are going out, so I am not capturing them, and the other photons coming out of the spontaneous emission is triggering stimulated emission, and those photons are also going in this direction along this axis. All right. Now, once some stimulated some photons coming out of a stimulated emission goes and hits here, then goes to this mirror through this active medium. All right. What they can do? I have already have population inversion. If suppose if it is a 4-level laser, I have the population inversion all the time. So this bunch of photon, after reflecting off this mirror, it goes and triggers more stimulated emission, which are just going in the same direction. So these photons are like multiplying. So they are trapped in this cavity, and they are traversing back and forth along this axis, and every movement through this active medium is creating more and more photon. So over a period of time, the number of photons within this cavity has built up enormously. All right. So, one set of simulated emission, when they are making this round trip, creating more, again more and more. Now, this huge amount of photon density inside this one, if they will go out if instead of this 100% reflectivity, if I make one of the mirrors, say M1, say 98% reflective, that means 2% it will transmit. What will happen? It will allow 2% from this edge, and that is my laser output. So, I build a huge population and then I allow some amount of light to go through, and that some amount is actually quite a large. Okay. So, that will have a very high density of photon. So, essentially the intensity of light will be very high. They are directional, so they are not going to scatter. So, they are very much directional, they are kind of collimated. All the photons have same phase, so they are coherent. Okay. So, they are giving you a coherent, collimated, high intense laser output. And this, what I showed here, is a continuous wave operation. I can do something to allow this whole built up here to go out in a very short period of time. Suppose I do something and once a huge number of photon density is created here, and allow all of them to go out at a time. So, creating a pulse, I can do that as well, and actually that is done very regularly. So, in the ND-YAG laser I can also do this, I can also get this pulsed output of very high intensity, very high power. Okay. So, we will talk about much more details in the coming classes. So, please stay tuned, and thank you for your attention. See you in the next class.